Okie dokie. It is that time. It is 7:30. So as per usual, hold on, let me change my screen really quickly. As per usual, I'm gonna go ahead and start talking. We have about like 20 people right now in the waiting room. So of course, if you've been here before, you know I'll probably talk for the first probably 2 to 3 minutes. Let me go ahead and pull up my key. We have been dropping the packet in the chat. I'll go ahead and drop it again. Okay, perfect. They're dropping it right now. If you do not see the packet being dropped, please message either me, Julia, or Will. Any three of us can email you the packet if you do not see it. So, also, let me drop one more thing really quickly. Not only is there the packet, but I promised y'all I would make y'all a little review sheet. So, oh, did that go in the chat? No, it didn't. Let me drop it again. Okay. Is it not going? Oh, I keep dropping it to a private message. Sorry, Haley. Hold on, let me get that in the chat. Okay, there it is. Go ahead and load that up and go ahead and kind of look at it in this first few minutes. Let me send this email to the one person who sent me their email. But yeah, if you look at that I kind of I just kind of went through the review that Dr. Gordon gave me and pretty much just, you know, went topic by topic, line by line, and just kind of put the main, what I found to be the most important things. If you came to my session Monday, if you combine that that review sheet with my packet from Monday and then do these practice problems today, I mean, in my opinion, that should have covered all the bases, I should say. I shouldn't say you're going to be in good shape because it is at the end of the day all on you. But definitely, if you study that, you're going to be in a great position. I literally spent like 2.5 hours today making that review sheet. So I kind of take a little bit of pride in it. So, okay, let me get that for you, Juliana. And yeah, how's everyone doing today? How are we feeling about the test? Obviously, almost everybody has the test tomorrow. So on a scale of 1 to 10, how are we feeling really quick like? Everyone seems pretty stressed. 8, 7, 10, 4, not terrible. Yeah, I feel like I kind of expected that for some reason for it to be a quite wide range of I feel super good and I feel really terrible. That's kind of because, at least in my opinion, this is kind of the first chapter where everything is really just conceptualized, really not a ton of math. I like to say that this kind of unit is kind of more geared towards organic chemistry in the sense of like everything is kind of conceptual, kind of just learning trends and that kind of stuff. It's really just kind of sitting down and memorizing it and just trying to see the trends. So if you're someone who doesn't like the math, generally you are the type of person who's like, yes, finally. And if you're someone who has been like loving the math and doing great, you may be kind of like, oh, this is too much information. So I don't know. There's kind of a happy middle where it's kind of a nice test because whether you are on the better end from the more math heavy tests, or if you're on the end where you didn't do so good on the test, this is kind of like an equalizer test, level playing field for everybody. So study hard. How was my day? My day was, I barely even remember my day. My day was good. Pretty much my whole entire day was making that review sheet. But I'm good. Tomorrow is my Friday Junior, so your Friday Junior as well. But yeah, I technically will have an exam tomorrow, but I studied a pretty good bit for it today, feeling pretty good. So yeah, I'm doing pretty good. Chris, let me get that for you really quick like, and then right after I do that for Chris, we are gonna go ahead. Oh, Chris, I think I already gave you that permission. Oh, that was from like way earlier. Okay, perfect. Then we're gonna go ahead and get into it. I'm gonna go ahead and share my screen and we'll start looking at stuff. We still have what looks like about 20 people still in the waiting room. So I'll probably kind of go back and drop the packet in chat as well as the review sheet here in a second. Someone remind me basically in saying that. Can you get the review sheet? Absolutely. Let me drop the review sheet in the chat one more time. Let me move these people out of my way. Sorry, sometimes Zoom can be a little bit much to deal with. Okay. Sylvia, give me a second and I may be able to, because I don't want to stop sharing my screen right now. So I'm gonna say no, not right now, but in a second. When I get the chance, I will stop and do that for you. Just PM me again in like 10 minutes, 5 minutes. Okay. But to quickly kind of summarize what we're doing today. So today is my favorite day personally. It is going to be the practice question day. Kind of set this up like a practice test. I believe we have exactly 23 questions on this practice thing. And typically the tests are about like 30 questions. I think someone had said 25 questions. Someone let me know in the chat if that's what they're saying right now. But yeah, kind of my plan for this is to give y'all about like, at least on the first page, 25 with 2 bonus. Okay, perfect. That's honestly perfect what I have today. So in saying that, I want to go ahead and just pretty much give y'all 8 minutes to do the first page. After the first page, we're going to have a little bit less questions per page, so I'll probably give y'all less time for those. But as far as for the first page, let's go ahead, give y'all 8 minutes to, just work that page, try to do as best you can. If you don't know everything, that is okay, obviously. But after 8 minutes, I will come back in and I will go over it. And yeah, we should be moving pretty quickly today. Hopefully some of this, what I expect is some of this to be super quick. We see it, it's easy. And then some of this, we're going to need to take a little bit longer on. So I'm kind of expecting that. So again, if you're doing super easy on some of them, but then all of a sudden hit a brick wall, that is okay. That is kind of to be expected. So that is about enough talking from me, I'd say. So let's go ahead and put 8 minutes on the clock. And I'm going to send y'all off. I just slammed my phone into the computer. But 8 minutes, go ahead. Good luck. Yeah, Kaylee, I had sent the review sheet in the chat, but if you don't see it, drop me your email. I'll drop it again, though. There's the review sheet. Again, if you have any questions in this 8 minutes, feel free to either drop it in the all chat or private message me. Do we need to know the lattice energy problem? I got that question. That's something that I put on my review sheet, but I don't even think I have a problem for lattice energy on this packet. Lattice energy, I believe we literally say it's the trend with the most exceptions. And so for that reason, like I believe even in the book, there's not like true worked problems. So I don't have it on here, and I also don't believe it's super relevant. So yep. Do you have a question about calorimetry? I don't believe calorimetry is on this test, so no, I do not have a problem over calorimetry. But if someone says that it is going to be on the test, I can absolutely at the end of the session work a really quick problem on calorimetry if we need it. You think it's the bonus? Okay. Well, if we don't run super over time, or if I finish just on time, if one of y'all has a calorimetry question you want me to work, go ahead and we'll just save it to the end. I'm not gonna say give it to me now, but save it to the end, and then I'll definitely look at that if we need. Yep, I'll put the review sheet in the chat, Kaylee. I think I may have just sent you an email, Kaylee, but no, I didn't. But I have been putting the review sheet in the chat. If you're not seeing it, drop me your email and I can send it to you. No, last time the QR code, I had a lot of trouble. Some people were able to access the link and some people weren't. So I just kind of did away with that. And that's why I'm just dropping everything through chat now. I mean, to study the wavelength stuff, I don't believe so. Pretty much the last thing on chapter 7 you should be looking at is quantum numbers. And Thompson's email said extra credit was solubility and frequency. Interesting. Wavelength might be the bonus. Yeah, if y'all want to do another question on that at the end, if we have time, definitely let me know. Okay. All right, perfect, Kaylee, I got you. Sending it to you right now. Yes, we all stand Julia. We love you, Julia. Haley, I think I may have sent you an email a minute ago, but if I didn't, go ahead and let me know what you still need from me. Julia is the GOAT. Been here forever. Perfect, Haley. Lara, as per usual. We stand Lara as well. Is that another person we stand is Miss Lara now? It looks like she probably dropped another one of her notes. I've heard pretty good things from them. She does it quite often, so I believe that they're reliable. So if you see Lara's document in the chat, definitely eat that up and use it as another study material. Always, always, always a benefit. So, yep, I got you, Mia. All right, y'all. Lara's going crazy right now. We're dropping some documents, so seriously, take advantage of that. That's extremely, extremely kind, really. So yeah, no, the definition of paramagnetic is just at least one unpaired electron versus diagmatic is every single electron has a pair. So no, technically, if we have an odd number of electrons, therefore there would be one that isn't paired. So if you do have an odd number, I'd say that still works for paramagnetic, but technically the definition is based off at least one unpaired electron. Don't all of them have paired electrons? So we'll see paired electrons based off of our like orbital diagrams. For example, like the D block has 5 orbitals representing 10 electrons. And so in every single orbital, we do like an up arrow for the first 5 times. That down arrow is that matching. So unless we have like a D10, it's gonna be it'll be paramagnetic. Only diamagnetic would be that D10. I don't know if that helps a little. Perfect. All right, you got about like 45 seconds left. You want me food? Thank you, Bebe. Thank you. Thank you. Thank you. Okay. Hi, Nick. What are the images being sent? I believe that those are just Lara's notes. Is the N for Nick on the wall? Yeah, exactly. That's his. That's some of his like. I'm not gonna say his artwork, but just some of his possessions, I guess. Hold on 1 second. Let me send this email. This girl is needing to get my link really quickly. Okay, that is the time though. Let me quickly ask while I'm just trying to send this email. How was that? On a scale of 1 to 10, how do we think it was? Okay, yeah, kind of a big variation as well. I still see a good bit of hard, which kind of little concerning, but we're gonna be okay. Hold on. Sorry, I had like 4 different people email me saying that they need into the SI session. I'm like, I don't control that. Okay, but let's go ahead and let me reshare my screen now that it is gone because I was AFK for so long. And then let's go ahead and jump into the first one. So the first one is just on quantum numbers. I believe it is. Actually, no, it's not. Sorry, the first thing on my review sheet is quantum numbers. The first thing on here is giving at least, it says give at least one example of an element that is expected to have similar properties as sulfur. Okay, so there's more than one answer for this in chat. So let's just go ahead and get some. What we got? Okay, so we got some oxygen, we have Se. Does anyone have any like other ones that they think maybe could be it? So I will, yeah, okay, perfect. TePO. Those are gonna be just the 4 I'm gonna go ahead and say. I'd say that anything past that, you are technically in the metals. Te and Po, again, I don't know the exact names for them. Those are part of the metalloids. Oxygen and selenium, those are part of the non-metals. So as we transition to the metalloids, we have properties of metals and non-metals, but past the metalloids, which is going down, we do become metals. So that's why I included Te and Po because they are metalloids, so they should still react similarly to the non-metals. However, I didn't include any strictly metals because those will just react quite differently. What does it mean to 5, or does that say S? That's an S. It's supposed to be sulfur. S for sulfur. Yeah. Alrighty. Hopefully we see that one. And again, the reason how we got these is just based off of the bonding that oxygen, sulfur, selenium, and Te. I don't know the exact name of that. Those are on the same group. So stuff in the same group will have similar bonding, and that we see that as well from their electron configuration. So in saying that, all 4 of these specifically kind of have like this bracket noble gas, and then they have, NS2, NP4 specifically. The N we're saying is variable. It is tellurium. There you go. It's Te. But all 4 of those will have, that they will have varying principal quantum numbers, which is that N. And then the S is representative of the S block, and then that P4 is representative that every single one of them is the 4th element in the P block. Oh, noble, LOL. Thank you, Caitlin. Noble gas, giving the condensed kind of short version of that. Okay. There's that off topic. What are we going to be tested on hybridization? I was kind of wondering that as well today because Dr. Gordon talked about hybridization, but I would not believe that they are going to be asking you about hybridization. Yeah, he was talking about how like on like a CCl4, which is like a tetrahedral geometry, that is sp4. And to quickly like explain why, if we have like CCl4, this is sp4, and how I like to think about it is I like to think about an s orbital can have 2 electrons and a p orbital can have up to 6. So like we can just say this is s, and then this is p3 because there's sp3 because there's 3 p orbitals, which is 6 electrons. So like 6 electrons contribute to a p, 2 electrons contribute to an s. So we have sp3 because we have 3 p orbitals and an s orbital. So kind of cash. It wouldn't be that hard of a topic to learn had you need to learn it, but okay, we're moving on though. Okay, so rank the following in order of increasing electronegativity. What do we have for this order? Yes, exactly. Y'all are doing great. Yep. So we have that it is an increasing electronegativity, meaning that our most electronegative will be on the far right, which you'll have right in the chat. It's going to be fluorine, but as far as my greater than and less than signs, I still want to show that fluorine is greater than with that greater or less than sign technically, meaning that it's greater than the rest. So there we go. This is it. Really simple as that. I will go ahead, and if you did have trouble on that one, the periodic trend, we do increase electronegativity up and to the right. So there is that. Is this like the test, or is it much difficult? So good question. So typically for my practice tests, I usually take literally exact questions from the practice exam. Last time I did that though, I had a few of y'all like, I'm not gonna say throw shade at me, but y'all were kind of like, man, kind of sad to have just worked this practice test and see these questions again. So today, all these questions are almost exact practice questions. I literally just changed the element. So in saying that, if you think that these are easy, these are literally exam questions that I literally just changed the element so that it's not the same question. So I did that to appease everybody. You're still seeing practice exam questions, but you're seeing, slightly different ones. So who throwing shade? I couldn't even tell you names at this point, but it was enough to where I was kind of like, okay, I'll be better in the future, Okay, moving on though. Which of the following would be paramagnetic? What do we got? What do we think? I'll pull up. Okay, we're doing pretty good. So a few of y'all had a few different ones, but we did pull away with the correct answer, which is going to be Ni2+. So for those that were saying zinc, if you said zinc, zinc is diamagnetic, and I'm going to do a very, very quick thing to show. So I'm going to go ahead and write, V, Ti, Zn, Mn, and then nickel, and then, yeah, that's all we have. Okay, perfect. And basically what I'm going to do with these is I'm going to be looking at the electron geometry, basically. So when we have cations, for example, Ni2+, that 2+ is representative of losing 2 electrons. So for V5+, Ti4+, what I'm going to do is go to the periodic table and just subtract those electrons, doing them in appropriate order. So I have it in front of me. Let's go ahead and look at V. So it's right here. Well, I'm just going to say, this is currently 4s2, 3d3. And we have 5+, meaning that we're going to lose 5 electrons. We see that from our superscripts, we only have 5 electrons that can be lost, right? Okay, so when we have a 5+, it's basically saying that we are losing all of these electrons. We no longer have this. We pretty much just have the configuration of argon because we lost those 5, the most outer electrons. We lost those 5, and so now we have 0 from the 4s or the 3d. So we take, yes, that's a great question, Salvador. Exactly. So for transition metals, we will always pull first from the higher principal quantum number, which is going to be your 4s or whichever one it is. But yeah, you'll always pull from your s first because that principal quantum number relates to distance from the nucleus. And so because we have a higher number of 3d compared to 4s, because that 4 is higher, that principal quantum number of 4 is higher, we will always pull those electrons first. But my point is, once we lose those 5 electrons, we have a configuration of argon. So I'm just going to go ahead and write, it has a very similar electron configuration as argon. This will be the same for Ti as well as Mn. If you go and look in the periodic table, for example, Ti, if we were to lose 4 electrons, we would lose this electron, this electron, this electron, and this electron, and we would be left with an electron configuration similar to argon. Okay? So, and saying that, now let's look at zinc. So it's saying that it is Zn2+. So with Zn2+, we quickly see that it is all, sorry, that was like a very dramatic oop. Zn is a 4s2 3d10. And so if you thought it was paramagnetic, that is because you probably you removed your 2 electrons from the d orbital. However, you should have removed your 2 electrons from your s orbital. And when you do that, you still have a complete octet, you still have a complete set of orbital numbers. So to quickly, 1, 2, 3, 4, we still have an up, down for all 5 orbitals representing the 10 electrons. So every electron that is currently present has a match. So that will make it diamagnetic, just as these other ones are diamagnetic, because every single electron is present isn't just by itself. So why would you take from the S? Okay, I think we got it. Okay, perfect. So in saying this, I'm going to say that it is giving the condensed form. We have argon as the most previous thing, but we do have 3d10 as now our valence electrons because we did take away from that 4s. So 4s2 just becomes 0 electrons. Exactly. Yep. So right here would be the condensed electron configuration of Zn2+. Okay, and then last one we have is the nickel 2+. And if we go here, we see that nickel, let me just quickly erase this just to keep everything kind of, easy to see for us. This is going to be our 4s2 3d8. Once again, we will be pulling from our s orbital first. So we will, just like the last case, we will say sayonara to our 4s2, and we are left with a 3d8. This is one of the cases where if you were going off of just odd numbers of electrons, it wouldn't hold true. But if we were to do our orbital diagrams, 1, 2, 3, 4, and we're going to go ahead and count out 8 electrons, we'd have 1, 2, 3, 4, 5, 6, 7, 8. And right here, you can see that both of those 2 electrons do not have a match. And so therefore, nickel is going to be paramagnetic. Does that make sense? This is one of the ones I was expecting to spend longer time on. So it's okay if you have questions and you're still not catching it, because I expected to spend a little bit longer. Donate higher energies electrons first. Exactly. Yep. And higher energy electrons are associated with your principal quantum number. Yep. So I have a private message. So if it was more than 2, we would take away from the S and then start taking away from the D. Exactly. Yeah. So if it was like, let's say, for example, zinc 3+, we would end up having 3d9. And at that point, it would also be paramagnetic. Exactly. Okay. So basically, you look at the electron configuration, and whichever one isn't a full set. Exactly. Yeah, exactly, Skylar. That's how I like to do it. Kind of my the quick way, I should say, is that your most last thing of your electron configuration, if that's not completely filled, you don't have a diamagnetic. For example, like if you don't have an S2, a P6, or a D10, if we have an S1, because it's not an S2, we know that the S orbital isn't completely filled. If we have anything less than a 6, because we have to do 1, 1, 1, and then go back and do 2, 3, up to 6. If it's not 6, there's one that's unmatched. Same with D10. If it's not 10, one is unmatched somewhere. So yeah. Would it be paramagnetic regardless, like just as Ni? Ni as itself would be diamagnetic. Oh no, I'm sorry. Nickel by itself would be paramagnetic, yes, because it would be 4s2 3d8. So you have that 3d8 still gives it that paramagnetic character. Exactly. Why did you highlight Zn as well? I think I just highlighted Zn just to show, I'll highlight it in a different color, just to show the configuration for it mainly. We stand Professor Creighton. Oh my God, thank you. Oh, Julia, that's coming from you? What the heck? Thank you, Julia. That is so sweet. Really? So let's say it's 4s2 and we take 3 away and we continue taking it from the 3s2 or move it onto the, so if we have a 4s2 and we're moving 3 electrons, we'll go ahead and remove those s2s. But if we have a d orbital, we will go ahead and remove from the d orbital. If 4s2 is like where we had stopped, then if we move that 3rd electron, that would come from the most previous. So if you're in the d orbital, if you lose 3 electrons, one of those will come from the d orbital. But if it's not a d block element, you will lose that 3rd electron from somewhere else. Okay. Does drawing the diagram of orbitals which are filled first help? That's how I would do it. I would draw the orbitals. Absolutely. Sorry, could you show why it wasn't V and Ti? Yeah, it wasn't V and Ti. Good question. So V specifically, we lost 5 electrons. And so originally this is 4s2, 3d3, right? The first 2 electrons that we will remove is going to come straight from our 4s2, which leaves us with our 3d3. Again, we have only lost 2 electrons so far. When we remove those next 3 electrons, we lose all of our d electrons. That means that we are no longer have any electrons in this period. we have a full set though of electrons all the way up to argon. And so in saying that, our most recent or our most outer shell of electrons now for V is going to be our p block, which is equivalent to our argon, which will have a full orbital, which is therefore diamagnetic. Okay. Hope that helps. What if nickel was 4,6D? Would it be paramagnetic? Yep. If nickel was 4,6D, it would be paramagnetic. Yep. Because once we have, because again, we have 5 orbitals for a D block. So we would have 1, 2, 3, 4, 5, and then 6. And then so all 4 of these would all be without a pair. So it would be paramagnetic. Okay. I think we're doing good. Super question, but is 4s2 a higher energy than 3d8? It is the higher energy than 3d8. Exactly. Anytime, your principal quantum number always relates to higher in energy. So 4 is greater than 3, so therefore it's higher in energy. I'm not going to call people out, but if you were thinking that 3d8 is lower in energy, you are wrong. Yep. Energy is always related to the principal quantum number. Even though we fill the 3d8 orbital after the 4s still has a higher principal quantum number, and so therefore is higher in energy. Yep. Okay. I expected us to spend a good amount of time on that. We kind of spent a little bit longer than I was planning, but I did account for that one to take a while. I'm going to go ahead and move on. If you do have more questions on that, please do hold them till the end. I think I did a pretty good explanation, but I would like to keep going. So which element in group 4A is the smallest radii? We already got one answer. Yep, we are doing good. It is going to be our carbon. So the trend for increasing radius is down to the left. Sorry. So that means that our smallest element is going to be up into the top right. So basically, when we are looking at just a group, we want to have the most high up in the period, aka the one with the smallest principal quantum number. So yep, it's going to be carbon. So give the ground state electron configuration of Br. Can y'all just type in chat the last period configuration? Is increasing radii the same as just size? Exactly, Haley. Correct. Okay, we got the 4p5 down pretty good. Okay, so I'm gonna go ahead and just write the red. I'm gonna write this in red just because, in my opinion, this is the more important part. From what Dr. Gordon said today, how they will be testing you on this is that you will have like a drop-down menu to be like 4s1 or 4s2, and you'll do that for like every little thing. But this is going to be the part that most people are going to mess up on, is that 4s2, that last period part. So that's why I want to do it in red. Just because someone probably has the question, the condensed form for this would be argon 4s2, 3d10, 4p5. So go ahead and check yourself with that. I missed 3s2. Oof, thank you. Clutch. (3s2), thank you for that catch, Hunter. Alrighty, I think we're probably going to be pretty good there. Ground state refers to total electron configuration. Exactly, David. Yep, and then condensed will be the one with the noble gas. All right, so it says give. So let me go ahead and just highlight this, just so this is the answer I'm specifically looking for. Okay, next question. Give both the electron and molecular geometries for the following compound. Isn't it 4p5? Oh, yeah, I don't know why I put 4p3. Yep, bromine is going to be your noble gas. Or sorry, not your noble gas. It's going to be a halogen representative of that group 7A, which is therefore a 4p5, because your 2s and your 5p should add up to the group number. So 7A. Correct. Thank you for that catch again. Cool. All right, what about this next one? What do you have for our electron geometry? Really quick, go ahead and drop that in chat first. Very nice. Okay, okay. I also appreciate that someone put in the chat that, but I'm gonna do that specifically for molecular. But it is gonna be trigonal bipyramidal, and the reason we know this, if you do have trouble still with these shapes, I do have the chart in my review sheet. Please go back and look at that a million times and get it in your head. But to find the electron geometries, all we do is just count the amount of electron groups. An electron group is just defined by any area of electron. So that includes single bonds, double bonds, triple bonds, lone pairs, or just a single electron. So in this case, we have a a group here, a group here, a group here, a group here, and a group here. So we have 5 groups that does correspond with trigonal bipyramidal. So if you're saying you thought T-shaped, you are not wrong. You're wrong, but you're not wrong. You're going to the right place. The electron geometry 100% is going to be our trigonal bipyramidal. However, our molecular geometry is going to be what? So you're just half stupid? Exactly. I'm just kidding. No, it's easy to get those confused at first. I really want to harp that, like, when you hear molecular geometry, like, just think of the molecules. Like, just keep it simple, stupid. Like, it's easy like that. Okay, it is going to be our T-shaped. Again, if you do want to, I highly recommend going and looking at that chart a bunch over and over and over and trying to see it. But again, to kind of explain the trigonal bipyramidal is we do have those 3 in the middle from like the normal trigonal planar, and then we put an electron pair at the top and the bottom, and that kind of gives us that pyramid. When we remove 2 groups, we're typically going to move them from the planar part, which kind of gives us that like outwards, up, and down, which all will be 90 degrees. So yeah. You're crying? What's the difference? Okay, the difference is that electron geometry is based off of all of it, versus molecular geometry is just based off of the molecules. So just based off like Cl, it just doesn't include those 2 lone pairs basically. Oh, who just, James? I would send all my screaming memes, Aaron, but I can't. We're gonna be fine. I do agree that probably the electron geometry and molecular geometry is gonna be like the one of the harder things on this test, so don't be discouraged. What chart? This chart right here is gonna be what you're gonna need for your electron group arrangement and your molecular shape. I pronounce it uwu as well, but people do pronounce it owo, but I say uwu as well. I don't say uwu, but if I was to pronounce the uwu, I would also say uwu. Okay. Which one of the following sets of quantum numbers can correctly represent a 3p orbital? What do we say? Said this was T-shaped? It is T-shaped. It is T-shaped. So, okay, we got pretty much very clear answer in chat. That is going to exactly be D. Okay, so quickly, the principal quantum number 3 is always going to be our N. I think we are seeing that pretty clear now. However, P, that is going to be associated with our L. And what exact value of L does P associate with? 1. Very nice. That's kind of a more trivial fact. So I'm proud of y'all who are knowing that. So in saying that, we go ahead and know that our N must be equal to 3 and our L must be equal to 1 based off P, which I'll explain furthermore in a second. But just based off that, anything that doesn't have a 3 or a 3 for an N, I'm going to go ahead and mark off. And anything that doesn't have a 1 as your L, I'm going to go ahead and mark off. Okay. Quickly, if you didn't know that your L is equal to 1, I have this also on my on here. If I can maybe find it super duper quickly. Ha ha ha. I think it's over. Did I not put it? Ah. Okay, perfect. Yeah. The L values 0, 1, 2, 3, 4 correspond to S, P, D, and F respectively, basically saying that S is equal to 0, P is 1, D is 2, and F is 3. So in case you hadn't picked that up yet, now you know. And then, yeah, someone had already started to say the imps of L in chat. That is always going to be from negative L to 0 to positive L. So someone had, there we go, exactly. So because L is 1, we have negative 1, 0, and positive 1. So anything that isn't one of those values, I know to cancel out. And so because we have an L here, an imp spell of 2, that is not going to be the answer. And yes, therefore we are left with D. So what is the M? What if ML was 0? Would that be unfair? No, I said it's absolutely fair. So to quickly kind of harp on imps of L and stuff, we have 3 values because that corresponds. So we're talking about the p orbital, right? The p orbital has 3 orbitals. I'm kind of saying that where the p block has 3 orbitals representing the 6 electrons. You can think of that as negative 1, 0, and positive 1. You can think of like each of those integers as a specific orbital. Same thing for like your d orbital. Like your d orbital corresponds your L would be equal to 2, which your imps of L would be equal to -2, -1, 0, 1, and 2. And in our D block, we have 1, 2, 3. We have 10 electrons. So this is like -2, -1, 0, 1, and 2. And so no, it wouldn't be unfair to ask for them to put 0, because you should be associating that every single one of those integers is technically associated with an orbital. So you could have an electron present in any of these, you know? So, okay, cool. Hopefully that kind of helped nail that down a little bit more. Okay, let's keep going. If they give us an element, we should be able to pinpoint the L value and the imps of S. Yeah, exactly. And you'll do that with your orbital diagrams. Okay, briefly describe the difference between electronegativity and electron affinity. I'm just gonna kind of, okay, Leo, we stand on you for being so prepared all the time. But yeah, I'm gonna give a very short answer. Again, on the test, the reason I'm gonna give a short answer is because this is very open to how you want to write things. And open-ended thing like this, I'm not gonna say there's a right or wrong answer. This is gonna be associated with electronegativity. Electronegativity is just talking about the trend, the tendency for something to do it, versus electron affinity is like a true quantitative value associated with it. So I'm just gonna say that this is a quantitative description of energy when atoms take on an electron. Okay. Laura instead of Lara, yeah. Okay, so that's pretty much cool. Again, the main thing is electronegativity is a trend. It is just the tendency for something to do it, whether it wants to do it and whether it does it commonly. Everything can take on an electron. We can force that, right? So like, again, electronegativity is just whether it wants to do it. The actual electron affinity is like, does it want to do it? And what's like that value, that energy value that is associated with it, really? So yeah, cool. I'm not going to talk about that too much more, but I'm going to go ahead and move on because we are moving a little slow. So what is the maximum number of electrons in an atom that can have the following set of quantum numbers? N is equal to 4, L is equal to 3, M sub L is equal to -2, and MS is equal to +1/2. Very nice. It is going to be 1. That's kind of a trick question. That is a question where if I was taking this test, that would be one of the ones I would probably have stumbled on and gotten a little uncomfy with. So proud of some of y'all for getting that correct. Again, I do want to just kind of redraw our orbital diagrams again, just because personally for me, it really, really, really does help. So 1, 2, 3, 4, 5. So how I'm gonna do this again is kind of going back on that. The L of 3 is representative of an F. So I'm gonna go -2, -1, 0, 1, 2. Sorry. -3, -2, -1, 0, 1, 2. I need to do one more box. And 3. Okay, so basically what it's saying is that we have a principal quantum number of 4, of course. The L3 is what we're actually getting to with our orbital diagram, which is an F. M sub L is -2. We're specifically talking about that -2 one, and we're saying it has a positive half. So basically we're saying that there's only one electron that can exist in that -2 with an up spin is really all we're saying. Anyway, we're going to talk about Pauli exclusion principle as well as Hund's rule a little bit in a second. So I'm not going to talk about those answers or talk about the definitions because they're going to be answers in a second. Okay. Is it 1 because it gives us the full set of numbers and there can't be more than one of the same electron? Exactly. Yep. There can only be one up arrow for that -2 orbital. All right. Next question. How many valence electrons does Ti have? What about all the electrons that come before that? All the electrons that would come before that would end up having a different M sub L or a different M sub L. So for example, anything that came before that M sub L is -2 plus half. The thing directly preceding that would have been M sub L of -1 with a positive half. Anything preceding it coming after it would be like an M sub L of -3 with a positive half. Okay, the answer to this is going to be 2. I do think it's going to be controversial only because I messed up a little bit on Monday and kind of suggested that transition metals, the whole period of the electrons, I said, or I had hinted that they could be considered valence electrons. However, the valence electrons, the valence electrons. Number is the sum of the electrons in the highest principal. Oh, that is not highest principal. Principal number, which is n. So basically, because Ti is equal to AR 4s2 3d10, because that 4s is our principal quantum number, only the things that has that 4 is going to be counted towards our valence electrons. So because the 4s only has a 2, we only have 2 valence electrons. And to kind of like further harp on this, if we go and look at nitrogen, actually, I'm not even going to use the example of nitrogen. I'm going to use the example of, I think that's like germanium or something like that. That is technically a 4s2 3d10 4p2. We understand that this still only has 6 valence electrons, which corresponds, or sorry, four valence electrons corresponding to that 4s2 4p2, also with that 4a. So from that, you can see that the 4s count towards those valence electrons, but that 3 does not. So hopefully that clears it up if you were one of the people that thought 4. And again, I had thought 4 a little bit the other night too. So don't feel bad. You're on 81. Yeah, if you thought it was, is Ti and TL different? No, I did have Ti. Yeah, if you had TL, whoops, sorry. That's your fault though, at Miles.
So are there cases where the S and P orbitals wouldn't contain the valence electrons in the highest level? Like if you were to do the condensed configuration to find it?
Yeah.
You know what I'm trying to say?
Yeah, exactly. So yeah, I mean, they could totally be like, give me the valence electrons of, Sn, and the condensed configuration of this would be 5s2, 4, oh, this would be specifically krypton, 5s2, 4d10, 5p2 again. And so in this case, yeah, we would still just take from our highest principal quantum number. Our subscripts are our amount of electrons. So yeah, because we have a subscript of 2 for our first principal quantum number and a superscript of 2 for our p quantum number, we have 2 plus 2 is equal to 4. So we'd again have 4 valence electrons for one of those. So I hope that answers your question. But yeah, they 100% could ask you to use the condensed configuration to find valence electrons.
Thank you.
Yep. Is copper 1? I need to look at copper on the periodic table. Good question, Chase. That was I know you probably messaged me. Sorry to kind of call you out. I didn't say your last name. But that's a really good question. So yeah, that's something that I don't think they're really going to test you on. Yes, for cases, for example, specifically, we will see it here as well as here. Anytime we have like a 3D4 as well as what would be expected to be a 3D9. So specifically, let's look at magnesium. That is typically a 4s2, or what we'd expect is a 4s2 3d4, and also for copper, we expect this to be a 4s2 3d9. However, in these two cases, both of these will pull from our principal quantum number of 4 to give us in the case of in the case of copper, well, 4s1 3d10, because it is so much more favorable to have a full complete orbital shell of the d orbital than it is of the s orbital. And so for that, because we were so close, we were just 1 electron away, as well as the 4s and 3d are practically on top of each other in terms of distances, it will actually pull one of those electrons from the s to supplement that one less. Same thing for Mn here. Having a half-filled orbital is also extremely beneficial. So here we'll have 4s1 3d5, again corresponding to a half-filled d shell, and that is another case. So yeah, and that's going to be the really only 2 cases are going to be Mn, Tc, Cu, Ag, which are going to be those 3d4 or those Nd4 and the Nd9. So
shouldn't it be Cr instead of Mn?
Say it again.
Shouldn't it be Cr instead of Mn, because Mn's already 3d5?
Oh yeah, if I did that, yeah, I definitely meant to put the 4th one, 100%. Yeah, again, those aren't just off the top of my head. I just know that when we do have thank you for that correction, by the way. A 3D4 specifically, that is when we would move it. So yeah, thank you for that. Yep, chromium and MO. Again, thank you for that correction. That's kind of an important exception. So, okay, do we ever take from d orbitals for v electrons? No, we will not. It's only been the case for like the 4 and the 9, only to get to that half shell and that complete shell. Technically, I say that if you technically Google it, there's actually a lot of cases where they pull from the s orbital to donate to the d. But as far as 1307 is concerned, you only need to know the d4 and the d9. So yeah. Okay, we're on the next page. I'm going to go through this page without giving y'all time to work it because I do think it is a more basicer page, as well as we have bigger and better things to get onto. So yeah, let's do the next page. Exactly. Let's go ahead and type in answers for chat. I think you don't, without even needing time, you can type the answer for this one. Which one do you think is the best Lewis structure for NH4? Exactly. Yep. Very clear and easy to see. Again, this is one that I pulled exactly from an old exam. This was not me changing anything. This is exactly given on an old exam. So if you think this is easy, it's going to be a freebie. But yep, again, we do want to abide by the octet rule. We see here that nitrogen has 2, 4, 6, 8, 10, 12 electrons. Nitrogen does not want that. Same thing here. We have 12 electrons on nitrogen. Here we have 10 electrons on nitrogen. Once again, here we have 10 electrons on nitrogen. Only here do we see we have a perfect octet of that 8 electrons on nitrogen, which is going to be our most favorable case. Okay, what combination of atoms gives a non-polar covalent bond? What do we got in chat? What do we think? CL. So yeah, it is going to be CL. If you put Br to Cl, I could see how you may think that because they are just stacked on top of each other, the same group. And so you would think their electronegativity would be very similar, but they are still a little bit different. Exactly. The key thing to be looking out here as Paige pointed out is that, yeah, our diatomics are going to be the ones where we have a non-polar. So I'm going to go ahead and write that non-polars are going to be equal to our diatomics. That is just a stellar case. It's easy to see. And once you see it, boom, you know it, be done with it. So yeah. For HCl, again, we do know those aren't non-polar because we do have a net pooling of electrons based on our electronegativity. So to quickly give our electronegativity, this is an increase to the top right of electronegativity. So we will point towards chlorine here, as well as we will point towards chlorine again here, because bromine is slightly down in the group and therefore less electronegative than chlorine. Exactly, chlorines both have the exact same electronegativity. All right, what makes molecules polar? Molecules are polar from an uneven distribution of electrons. We see this again with cases of differences in electronegativity. Because chlorine is more electronegative, it's going to hoard those electrons. And because it's hoarding the electrons, just by that side is just naturally going to be more negative because it has more electrons. And that creates a polarity, a pooling of electrons. Okay. Moving on, let's go ahead and work this. Go ahead and type in the chat what we have for this. 24 is going to be the correct answer. Thank y'all. So to quickly do this, I'm going to, again, try to save time, kind of catch us up a little bit. I'm going to write it out and then explain it just so I'm not stumbling over my words as I'm writing something. Okay. And we do have this is equal to 24 valence electrons. So what I'm doing here specifically is that all I'm doing is taking the amount of each atom and multiplying it by its respective amount of valence electrons. So for example, here we see we have 1 carbon. So I have 1 carbon with 1 multiplying by its 4 valence electrons. So again, we have 1 carbon with the 1 multiplying by 4, representing its valence electrons. Moving on, next we're going to have 3 hydrogens. So specifically, I kind of flipped it here, but we do have 3 hydrogens being multiplied by their 1 valence electron each. The next one, we will have 1 nitrogen. So here we have 1 for the 1 nitrogen and the 5 for the 5 valence electrons associated with nitrogen. Last bit, we do have 2 oxygen. So again, having that 2 for the amount of oxygen and having that 6 for the amount of valence electrons that each oxygen contributes. So again, multiplying those out and summing each individual multiplication did give me 24 valence electrons. So one quick question. If we had had CH3NO2 minus, how many valence electrons would we now have? I gotcha, Mark. Yeah, so it's kind of a trick question. The minus makes you think you're going to end up subtracting, but do remember that the gain of a negative is a gain of an electron. So if we did have a negative there, we would end up having 25 electrons because we do have a net of 1 extra electron. Sorry to call you out by name. Won't say your name again, but sorry to call you out by name. Okay, let's go ahead and move on. This is a multiple choice question. Let's see, let me look at questions really quickly and see if we had any. Yep, the answer in chat that's pulling away is not going to be the correct answer, actually. Why is there only 1 mole of hydrogen? Shouldn't there be 3? Oh, yeah, I just flipped this. Yeah, it is 1 times 3 still, but it is technically 3 times 1 specifically. I just had it flipped. Math's still the same. Okay. It's going to be 5, though. Thank y'all for those who ended up putting it out there. Yep. So it's going to be 5. Again, to quickly draw these out, we're going to have this as an S, this as a P. 1, 2, 3, 4. This as SP, this is a D. And then our F is actually super, super long. We got 1, 2, 3, 4, 5, 6. And this is our F. So to quickly count, we see that the S block just has 1. The P block has 1, 2, 3. The D block has 1, 2, 3, 4, 5 orbitals. The F block has 1, 2, 3, 4, 5, 6, 7 orbitals. So exactly. Yup. And if you did D is equal to 3 and then it did M sub L from there, that is the thinking we need to be on. David, I'm extremely proud of you for having done it that way. That is the level of thinking we need to be getting on, of correlating everything together. So great job, really, truly, like not even sarcastically. So, okay, great. Let's look at this last one. Yeah, good job, David. Like actually, like truly pat on the back for correlating that. The effective nuclear charge for an atom is less than the actual nuclear charge due to blank. Yep, it is going to be shielding. This is another question that I did pull straight from the practice exams. However, I did pull it because I just want y'all to associate shielding with effective nuclear charge. Even in my review sheet, I don't even believe I gave y'all 2 different definitions for effective nuclear charge. I believe I literally gave them in a definition together. I literally can't find it at the moment, but somewhere in here, if you do find effective nuclear charge, you will find shielding right there with it. So again, it's probably going to be an answer on the test, but just associate them together is going to be my my word of advice. First page says shielding. Thank you. Somewhere on there. Oh, yes. See, look, I got shielding and then effective nuclear charge. I put them together to make sure that you know that they are associated together because it's probably going to be an answer. Okay. I have an extra question on my page. I believe on your packet, there may not be a question on here. Maybe there is, maybe there's not. I'm not sure. Okay. Which of the following sublevels is filled last? So we got some 5S's. We do have a good bit of 4Ds. I still see a little bit of 5S's. Will the wavelength be on the exam? I've heard that it's going to be potentially should be a extra credit problem. All right, very nice. It is going to be 4D. It's kind of the way to think about this is that if we had 3D, 3D10, we would then, go back up to 4P6 or 4S2, 3D10. And then we would go to 5S2 and then 4D10. However, and saying that, which of the following is filled last is going to be that 4D because that is how it is on the periodic table as well as the way it is filled. So don't be tripped up by them giving you those listed in increasing principal quantum number because do see that I did put the 3D between that as well as then I did move that 4D, or sorry, that 5S between those again. So try to rearrange it and then see which one is last. But valence is 5s2. Exactly. The valence is going to be 5s2. However, that valence is already going to be there. So if we were to, have a D block up here, we're going to fill our S before we will fill our D. And so it's just going to be there first. And so therefore it's just we will fill the D last because we have to fill the S first just based on the elements that are present before it. So hope that maybe helps a little bit. But yeah, we will fill the 4D last. Okay, I think we are kind of getting back on track a little bit. We've got about 30 minutes left with a page and a half. I do want to try to give you a little bit of time to do this page. I think I'm only going to give you I feel bad about giving y'all 5 minutes, but I'm going to give y'all 5 minutes and I'm going to say do this one last because that's going to be the most time consuming. So yeah. What's the difference in IE1 and IE2? IE1 is the removal of the first electron. IE2 is not only the removal of the first, but then removing a second electron. I thought I just knocked some food over. Okay. Oop, David left. See, that's fine though. I'm not insulted. Okay, I'm gonna give you 5 minutes on the clock again. If you got questions, drop them in either the all chat or the private chat. But 5 minutes, go ahead, y'all. Good luck. You say, well, I think if you're actually say forming is negative, right? So all I'm going to say, I don't know exactly what terms you're saying this, but as far as bond breaking is endothermic, bond forming is exothermic. So that's all I'm going to really say on that, but that should tell you your negative sign. Correct. Electronegativity and electronaffinity do indeed have the same periodic trend. That was a private message I got. It takes energy to break things. Exactly. Can we do divided shared electrons by 2 instead of multiplying it for formal charge? Yeah, I multiply by half for the share, but if you want to divide by 2, if you think that's easier to not have a fraction, go for it, Lara. Absolutely. Is the third question unfinished? Oh my God, stop. Wait, which question? Oh, it may be for you. It depends on which packet I gave. There should be a structure. My first packet, Jackson, I think you're the person who I email the packet to normally before yeah, you may have a different packet than what's on here, but you should be seeing the oxidation number of oxygen and then a little structure. Yeah. Absolutely. For the person who PM'd me, I'll go over it more in depth. Yeah. You can't remember the difference between formal and oxidation number. One hint that I will give you is that oxidation number will always be the number you expect it to be from the periodic trend. For example, like O, we expect to be like O2 negative. And so in saying that, you should be, however you're working it, you should be getting it like that. I'm not gonna tell you the formula because you're working it, not me right now, right? But to kind of give you, to see if you're doing your work right, your oxidation number should come out to be what you expect from where it's positioned in the periodic table. Okay, and let me send this email. Absolutely against the person who PM'd me. Yep. Okay, that was the 5 minutes. How do we feel about that one? Out of scale of 1 to 10 again, what do we think? Do you mind going in depth on formal charge? Absolutely, we're Gucci. We're good. I hate saying that word, but we're good. Okay, we got some 2s, we got some 10s, we got some 5s. Again, all across the board. We got an 11 in a private chat, a 50 in the all chat, bold. But okay, I'm not going to talk too much about the numbers, and I'm just going to go into it. Stupid question for double bonds. Would it be 2 sticks? Exactly, correct. Let me find my pencil for a second. Okay, let's start with number 1. All right, which of the following elements has the this one's probably going to take a second to explain too. So we only got 20 minutes. Hopefully we'll finish this page. If we don't finish this page, it won't be the end of the world. Which of the following elements has the largest second ionization, i.e. 2? I'm going to explain this a different way than I explained it on Monday. And hopefully this way goes a little bit better. We will see. Because the other night was rough trying to explain it. I think I did a really bad job, actually. Okay, but the answer, I'm going to go ahead. Well, I'm not going to even answer it. I'm going to explain it first. I think that's going to be better. Okay, so basically what I'm going to do for this, or how I'm going to explain it now. First thing I'm going to do, I'm going to erase pretty much my entire periodic table because we're about to be kind of a mess. Not like an actual mess, but do try to keep up with what I'm saying. Okay, so let's see. We have, we're starting at boron, oxygen, fluorine, lithium, and sodium. Okay, and we're looking at which has the largest second ionization energy. So basically, when I do this, I don't give 2 booties what the first ionization energy is. I only give what the second one is. So what I like to do is, what I'm going to do now is draw arrows from where it started to where the first loss of electron goes. And then I'm going to draw another arrow from where we are after the first loss of electron to where we end up after the second loss of electrons. So bear with me. Again, just kind of follow what I'm doing, and we'll be good. Okay, so we're going, starting at boron, we're going to lose just 1. I'm going to say this is IE1. Cool. We're going to go here, and then we're going to go jump from here to here, and we're going to call this IE2. I'm going to use electron. It's going to be its IE1. It's going to go to nitrogen. At that point, it still has another electron to lose. Once it loses that electron, it'll now be in an electron configuration of carbon. Same thing for fluorine. Let me go ahead and just do this in a different color. Let's do it in the green. I'm going to do it a little bit quicker. We got IE1, IE2. I'm just going to go ahead and say 1, 2. Okay, let's do it for our sodium and lithium. Let's go ahead and once again change colors. That was an interesting noise. I'm going to do it, this kind of going off the page. Lithium is first going to go to helium as its IE1, and then its IE2 must lose a second one. It's going to jump all the way over to hydrogen. And then same thing with sodium. I'm going to kind of go back because after we lose 1 electron from that S, we will go back to the most previous noble gas. So that is IE1, and then our IE2 will be jumping from neon to fluorine of that IE2. Sorry to do a second color for the sodium. Okay, so now that I've drawn that out, we're comparing the energies. Sorry, I'm not reading chat. I have it kind of like blocked off for me. It takes a ton of energy to remove an electron from a noble gas configuration. Exactly, Max. No, 100% correct. Exactly. That's the point that I'm going to try to get to, is it takes a ton of energy to remove an electron from a noble gas. Also, in saying this, the trend for ionization energy, I'm going to put it here just so we know. The trend for ionization energy, it increases up until the top right. This is for ionization energy, not for ionization energy 1 or ionization energy 2, just for the removal of an electron. So in saying that, because we are removing 2 electrons, I want to compare where everything is before it loses that last electron. So basically where I'm going to look at all my jumps. So specifically for oxygen, we're jumping from nitrogen to carbon, right? For fluorine, we are going from oxygen to nitrogen. For boron, we are going from beryllium to lithium. So we're at beryllium. And then from lithium, we're going from helium to hydrogen. And from sodium, we're going to neon to fluorine. So, and saying that, I just highlighted the elements. Again, you can kind of see that their arrows, it's going from the IE1 to the IE2. Same thing here. Oxygen, it's just before. We want to compare these because these spots are the accurate representation of what that next removal will look like. So in saying that, this is the best way to compare our IE2s, in which case we will say that lithium has the highest IE2 because it's going to be nearly impossible to remove an electron from helium versus removing an electron from neon to go to fluorine. It's still extremely hard, but slightly less hard, as well as removing an electron from going from oxygen to nitrogen is, again, slightly even less hard. And then jumping from that nitrogen configuration to that carbon configuration is, again, even less hard. Does that kind of help compared to the other night, kind of seeing it? Let me know. So in saying that, lithium should be your answer. Yep. Makes more sense? No, doesn't make more sense. Yes, it makes more sense. Why are we jumping twice? We're jumping twice because we have 2 electrons removed. Again, we don't care what the energy from the first electron removed is, because we don't care about, for example, this, this IE1, I go ahead and just shift my element once so that I can compare this ionization energy, the IE2. Does that maybe help a little bit while we're jumping twice? I jumped the first time so we can just compare a singular ionization energy and not be like thinking about a second removal when looking at them in the periodic chart where they're typically at. So lithium landed on hydrogen. Exactly. It's electron configuration because lithium is technically a 2s1. And if we remove 2 ionization, if we move 2 electrons, this will take us initially to 1s2, because again, that is -1 electron. And then minus another electron is 1s1. And 1s1 is equal to hydrogen. That is the configuration of hydrogen. Exactly. It takes more energy to remove an electron the further right you go. So our noble gases are going to have basically it's going to take the most energy to remove an electron from a noble gas. Correct. Why wouldn't it be Na? It wouldn't be Na because they both end up here, hydrogen or helium and neon, and our periodic trend says that ionization energy increases to the top right. So even from IE1, lithium has a higher IE1 than sodium, as well as it has a higher IE2 than sodium. What is the answer? The answer is lithium. Does that kind of answer your question, Alexandra, that it wouldn't be sodium because just from the beginning, lithium is higher up, so therefore it already has a higher ionization energy? You're lost, Robert. I expect IE2 to be the hardest thing on the test. I expect literally more than 50% of the class to miss ionization energy 2s. The reason that I'm trying so dang hard to get this is because it's something that I missed and literally like 70% of 1307 traditionally misses. It's a concept that is extremely hard and abstract, but getting this right is the questions that get you the A. Again, there's only 25 questions. You missed 3 questions, you're at a B. Getting the IE2 question right is a big deal now. So that's kind of why I'm trying to really get y'all there. So yeah, send me an email, Robert. I may even be able to explain it a little bit better on email now that I'm moving on. But I am going to move on because I do want to try to keep going. It's IE2 because it says second, right? Exactly. The second ionization energy is going to be, or the second electron removal is the IE2. Correct. Are these trends on the review sheet? They should be. Yes, ma'am. Or yes, sir. Sorry. Okay, I'm going to go ahead and move on to this one because, again, we only have 15 minutes left, and I know a lot of y'all want to see more. Hold on, I'll answer one more question. So if I got pushed off the cliff, it would be IE1, but if I rolled after falling, it would be IE2. I would really say like IE1 would be like rolling. It's not a lot of energy to roll, but falling is like a lot. You're going to see a large gap. To also, I should have brought this up earlier. Please look at this chart in my review sheet. If you're having trouble seeing like this huge jump, we see here that IE1 for lithium is 0.52, and it has a literal massive jump. That's because lithium, after you lose one electron, it becomes like a noble gas configuration. We have a huge jump because once we're like a noble gas, it doesn't want to lose an electron anymore. So we have a huge jump. This is super, super good chart to try to see those trends. Will this chart be given to us? Absolutely not, Eden. Definitely not. No, definitely not. But IE by itself doesn't move. Exactly, Reagan. So why would IE move twice? Ionization energy is a trend. IE2 is by definition is the removal of 2 electrons. Again, IE is a trend. It's how hard something is to remove. It does have a quantitative value, but IE2 is the removal of 2 electrons. We're asking about the ionization energy associated with that second electron being removed. We're still talking about ionization energy, but we're talking about the energy of the second electron removed. So we call it IE2 to understand that it is still ionization energy, but not ionization energy of the removal of 1 electron, the ionization energy of the removal of 2 electrons. Okay, truly moving on. Truly. Which of the, in the following structure, give the formal charge and oxidation number of oxygen. Go ahead and let's drop in the chat some of your answers. Okay. All right, formal charge. I'm going to write oxidation number. Okay. So yep, the numbers that we're getting look pretty good. I'm going to go ahead and write the numbers just because I want to write and then explain, just because I think that helps me personally go a little bit smoother. But you should be getting from your formal charge that the oxygen is a +1, and you should be getting that for your oxidation number. You should be getting a -2. Okay. Yeah, I'm going to do that probably last. I may not even do that because we have 12 minutes left. And that's something that truly you can look at the key, and I didn't even teach this in SI because I think that is such a basic concept that you could see it once and do it on the test flawlessly. Okay, but I'm going to talk about formal charge really quickly. So formal charge is equal to the valence electrons minus our unshared plus half of our shared. I also like to say that formal charge is equal to our valence minus our sticks plus our dots. So in saying that, of course, oxygen always contributes 6 valence electrons that come straight from the periodic table, but the unshared, we have 2 here, and that's because we have we have 1 pair of electrons, of unpaired electrons. So there's 1, those are unbound, and then we have 6 shared because we have 2 for each bond, 2, 4, and 6. There's 3 bonds representing 2 for each. And then part of that equation is half of the shared. So that's how I get those exact numbers. Sorry, I think chat's moving pretty quickly, but I think y'all are taking care of it, so I appreciate y'all. Yeah, also to kind of further harp on the sticks minus the dots, this would also be 6 minus 2 from the dots, 1, 2 dots, plus the sticks. We see 3 sticks representing the 3 lines, which again still gives us that +1. So if you want to do 6 plus dots method for formal charge, go for it. Oxidation number is going to be equal to your valence electrons minus your unshared plus your shared. However, the main thing to remember, yes, I'll give you, yes, Jasmine, anything that I don't go over, I will show you the answers. I know not all of us do that. Technically, I can get in trouble for it, but I will show you all the answers. And saying that, what was I going with that? The thing to remember is that for oxidation number, the more electronegative atom always gets all the shared electrons. And so in this case, oxygen is more electronegative than hydrogen as well as carbon, which is what's represented by the rest. And so for that reason, oxygen will get all of these shared electrons and not be dividing by half. So in saying that, okay, perfect. Thank you, Will. My boss just said I'm not getting in trouble, so pog. But in saying that, we do see here that the oxygen is the more electronegative, so it will receive all of those shared electrons. Again, we do have 2, 4, and 6 from those 3 lines. So in this case, we won't be dividing that 6 by 2 because oxygen is more electronegative and therefore gets to keep all of those electrons. So yeah. Does that kind of help with that for the person who was asking me to kind of go a little bit more into oxidation numbers? Poggers, yeah, I probably say a lot of Twitch emotes. I say like lol, poggers, pog, those are PogChamp, all Twitch emotes.
I have a question real quick. Sorry.
Go for it. No, you're good.
For the shared electrons, like the lines, how do you get 6? Or like I'm stupid or something.
So are you talking about specifically for oxidation number?
Formal charge, sorry.
Oh, formal charge. Okay, great. So it's gonna actually be the same kind of deal. Every single line is equal to 2 electrons, every bond. So this is a single bond is equal to 2 electrons. And then for example, a double bond, I'm gonna draw it a little bit skinnier. A double bond is equal to 4 electrons because again, we're getting 2 from here and 2 from here. So specifically in here, we're getting half of the shared. A shared is anything that is covalent, right? And so we have 2, 4, and then 6, representing 3 bonds. Each bond has 2 electrons. So therefore we have 6 shared for both cases. So in the formal charge, we're dividing these shared by half, or timesing it by half, sorry. Versus in the oxidation number, we are not multiplying it by half. But the shared should still come out to be 6.
Okay,
So.
that makes so much sense. Thank you.
Absolutely. Thank you for asking. Okay, moving on. We got 7 minutes. What is the molecular shape of BCl3 as predicted by the Vesper theory? So first step to kind of doing this, go ahead and be typing out your chat or your answers. First thing I would be doing is going ahead and figuring out the amount of valence electrons. To do this, you do need to try to figure out the Lewis structure, which the first step of that is going to be figuring out your valence electrons. After that is basically making, sorry, that seal on that bottom is kind of ugly, but is making your actual structure. We always start by putting our least electronegative atom in the center and then bonding it to the outers, which is going to be the Cl. We subtracted 6 for each of those bonds. So we end up with 18 electrons left, and then we add them to the more electronegative atoms first. That end up using up all those electrons. I had 0 left. And so chlorine has a full octet, this chlorine has a full octet, and this chlorine has a full octet, even though it's kind of ugly. But boron is going to be one of those cases where we don't actually have to have a full octet. So we are good here. And then from there, all you do to find your molecular shape is just count up your bonding regions as well as your non-bonding regions. We have 3 bonding regions and 0 non-bonding regions. So exactly, that is going to be our, I'm going to do it in red, our trigonal planar. Very cool, y'all. You like that molecular shape? Yeah, we like the planar ones, I think. Someone wanted me to go a little bit more in depth with the Vesper theory. I don't think there's really much room to kind of go into depth with it. Here in a minute, when I kind of get to the end of this, I have a website that I really strongly recommend y'all go and just kind of mess with. You can just add bonds and electrons and just see how the structures change. Looks like Andrew just put some notes in the chat to help with the FSEPR. Y'all eat that up. Free notes. Like that's my like that's really, really clutch. So really take those. Okay, I'm gonna go ahead and move on. We have 5 minutes. Which of the following molecules is polar? What do we got in the chat? Not me downloading all the notes and not looking at them. That would be me too. It is going to be SF2. It is, so yeah, CO2 is actually going to be just linear. Kind of the way to think about that is, or at least how I think about it, is that carbon can have 4 bonds. Oxygen has 2 negative for each of them. So it wants to gain 2 bonds, right? So both oxygen will be doubly bonded to carbon because carbon wants to make 2 bonds and oxygen wants to gain 2 electrons. So just from kind of like conceptually thinking about it, you can kind of see that CO2 is going to be linear. But hopefully from doing these, you would start out by just kind of finding the valence electrons from this. Of course, this is going to be 1 times S. I am telling you that the answer is SF2 if I didn't already state that. And then we have 2 times our F here. So we have 20 valence electrons. I went ahead and just put my least electronegative atom in the middle, which is going to be my S. After that, I go ahead and subtract my amounts of electrons for my bonds, which leaves me left with 16 electrons. I then go and fill in my more electronegative atoms first. So 2, 4, 6, 8, 10, and then 12. We're left with 4 electrons, so we can just put them first on sulfur. Then we go back and see, does everything look good? All right, fluorine's got 8. Okay, that fluorine's got 8. Okay, and that sulfur's got 8. And we see that we have an excess of electrons at the top. So therefore, it's going to be polar. We're going to have a dipole moment running straight up through it. Do you have to draw structures for this problem? You don't have to. Like some of them I can pretty quickly like eliminate, like CCl4. Hopefully you can see that that's going to just pull in all directions. That's non-polar. I personally think that CO2 we can see as linear, which that would lead me just to BeCl2, KrF2, and then CF2 or SF2. For those, I would try to make the Lewis structures just to have the highest confidence for me.
Can you draw the KrF2 out, please?
Sure. Yeah, I'm gonna go to the next page and do it at the bottom really quickly. Okay.
I have a question. Why did you subtract 4?
Good question. So that's actually just part. I'll do KrF2 in a second. That is just kind of part of our building Lewis dots or drawing Lewis structures. If we go in so I go in this order. The first thing I do is place the least electronegative atom in the center. I then add up my valence electrons. The next step, step 3, is draw a single bond from each atom to the central atom, and then subtract 2 electrons for each bond from the total number of valence electrons to the number of electrons remaining. So that's just why I do it, just so I know how many dots I can put around. So we have initially, 20 valence electrons. We made 2 bonds, so I know that I have 16 electrons left that can be placed as lone pairs around the rest of the atoms.
Okay, that makes complete sense. Thank you.
Perfect, absolutely. All right, so let's look at KrF. So there's going to be 1 krypton, which will contribute 8 electrons. This is going to be probably more of a difficult one just because krypton, as we know, is going to be a noble gas. I actually haven't done the electron configuration from this yet, so bear with me if it takes me a little bit. Maybe not going to take me a little bit, but if I want y'all to help me a little bit. Okay, so we have 14 plus 8 is going to be 22 valence electrons. After that, I'm going to go ahead. I'm going to put krypton in the middle. Fluorine is not going to be your central atom. It is just not. After that, I'm going to go ahead and I'm just going to do it like this. Place fluorine on the sides. I'm going to go ahead and subtract my 4 electrons. That's going to give me 18 electrons left. I personally am going to put them on the more electronegative atoms first. So I'm going to go 2, 4, 6, 8, 10, 12. We have 6 electrons left. So I'm going to go 2, 4, and then 6. I'd actually probably say that is just the structure. Yeah, because fluorine wants to have an oxidation or a formal charge to 0, which in this case it would, as well as it's going to be the case where it wants to have an octet the most. Krypton is going to be one of those cases it can have an extended octet, so we're pretty okay having lone pairs on the outside. And because there's 6 of them, that does give us that case for that trigonal bipyramidal geometry. So for that reason, I would assume KrF2 is going to be the answer, but I just want to look it up really quickly. Can anyone like tell me if that is the answer really quickly? Or if that looks correct? Yep, it is correct. Perfect. I did it right. Just want to make sure. I just so I'm not like telling 160 people the wrong answer, right?
How do you know that that's not going to be bent?
How it's not going to be bent? Well, that's kind of that's a good question. I would really just kind of say just keep looking at your chart. You're just going to need to start adding up the amount of electron groups. So for example, in this example, we have 5. 3 from the lone pairs, 2 from the bonding. So we know we're at least going to have, the trigonal bipyramidal electron group. However, we have 3 electron pairs, which leaves us with 2 molecules, which here is just this. And so it's just linear. As far as like the shape, I would say that the T shape, the linear shape are going to be the hard ones, because it's kind of hard to conceptualize where we're losing electrons. So for that, I would really just recommend just kind of memorizing this table is really the best advice I can really give for seeing those shapes when it comes to 5+ electron groups. So, cool. I'm trying to see, do we have any more? Okay, no problem, Julia, I'll watch it. So why is this one not polar? This one's not polar because our planar part is the electron pairs, and then our like linear part is straight up and down. So we don't have all of our planar part is all pulling equally in the center, and then our 2 like fluorines at the top and the bottom are also pulling equally. So we basically just have stuff pulling at all ways, which makes it non-polar. If that helps. Next page, please. Absolutely, Max. Moving. We're doing it. I'm gonna go ahead and put up the answers. It is 9:01. Time has really run away. We got pretty close to the end. I'm gonna I'll just go ahead and put it up. Yeah. I don't think this page is even really that hard anyway, so it won't be too bad. Molecular doesn't include lone pairs. Exactly. Electron does include lone pairs. Electron geometry includes lone pairs. It includes any type of electron group. Okay, so for this one, basically this is just saying that N is equal to size, L is equal to shape. M sub L, I don't even technically know what that is, but M sub S is spin. So that's just kind of conceptualizing it. I will say that this is actually just flipped. Do note that the principal quantum number is associated with the period number typically, as well as the L, the angular momentum quantum number, is associated with the period block, the SPD or F block. Moving on, the orbital diagram associated with nitrogen is going to be A. The bottom one is the only one besides A that doesn't have any exceptions. However, it is the case for oxygen. B, it does violate Hund's rule. That is because we have a down arrow before we have an up. So that is the violation of Hund's rule. And then the C violates off-balance principle because we should have had a down arrow here before we had an up arrow filling the other one. Okay. And the last one is the 5F. The main thing is to note that F is associated with L and that M sub L is -3 to +3, so on and so forth. Yeah, that's kind of the pack, y'all. I'm gonna actually put this up really quickly and quickly talk about it. This enthalpy, this is basically what we do here is we're just looking at what is changing. We have CH3s are remaining the same. They're giving us down here enthalpy changes. So what I do is I have C to O, as well as I'll say that this C to C is consistent as well. But we have a C to O that is only present once. We have a C to O here, singly bond, that isn't always present, an OH which is always present, and then this specific CH is new. In this, we want to do products minus reactants. So what we do, to quickly explain, yeah, if you're heading out, y'all, thank you for staying. I hope you enjoyed. Good luck on your test, y'all. But for those who are still here, quickly explaining, this 745 is, again, this is from the product side. This is C double bonded O. There's only one of them. And then as well, we do have this H2, which is H to H. So basically, we're putting on each side stuff that is not always present, stuff that is changing essentially. So on the product side, we have CO that is changing, and that H2 is going to eventually become part of the structure. So we're going to put those, and then we're subtracting it from the reactants. That 467 is that new OH bound. that 358 is going to be the new C to the single bonded to O, and that 413 is going to be that C to H. All it is just a very simple addition subtraction there. And that should be getting you that -61. Because I didn't talk about that a lot today, as well as I didn't technically go over that in the SI sessions of like normal weeks. If you do want further clarification on that one, absolutely please email me. I don't want to leave y'all hanging. Your test is tomorrow. So if you do have questions on that, I do think it's easy. If you just do a few of them, but if you do have questions on it, please just email me. So we only do the ones that change. You can technically do every individual bond, but at that point you're gonna have like 9 or 10 additions, and at that point it becomes super easy to mess things up. I'm gonna go ahead and start scrolling kind of through this in case you did miss anything or kind of came in late, because I know a lot of y'all kind of did, because the room kind of got really crowded. So okay. Absolutely, Juliana. Is there an SI tomorrow? I believe there is. I believe Michaelin has an SI session tomorrow. Someone in the chat, correct me if I'm wrong, though. I know Elliot's done for the week. How do you figure out largest lattice energy? Well, lattice energy is typically accompanied with the Born-Haber process, if I'm not mistaken. Let me just make sure. Yeah, lattice energy, I wouldn't even really worry about, but this is going to be the trend for knowing which is the largest lattice energy. The size is going to be like kind of the trump all, so I'm going to circle that in red. Size is most important for determining larger lattice energy. So that's going to say for that. I'm confused. I thought the CHOH would be products. Let me go back to it. Oh, let me go to my key. I was like, why is it not on here? You thought that the CHOH would be on the products? No, yeah, it is on the products. Exactly. Oh, shoot. I think this is supposed to be reactants minus products. Fudge, everyone just left too. Oh, I may have to send an email to correct that. Frick. I do think that it should come out to -61, but yeah, 100% the OH should be with products. Can you see the last one really quickly? Yeah, I'll put up everything. I'll kind of scroll through it. Let's see. What is the test over? The test over the last section of chapter 7, which is quantum numbers, and then all the way through chapter 10, 8, 9, and 10. Michaela's 436. Perfect. Thank you, Claire. I am getting Discord ping. Yeah. Maybe from someone in the session too. You got -61. Did you get -61 from products minus reactants or reactants minus products? What about 11 and 12? 11 and 12 will be on the final. Yeah. Thank you, Will. He should do Chem 1308. I don't know. I mean, I have the packets for it. I do have the packets for it. We'll see. This has been a really good group of kids. I'm like actually kind of sad to see like this semester coming into an end soon. Can you explain the last part of the last question? Absolutely. Please do 1308. We'll see. I don't know. We'll see. They are looking for a position for it. So it was reactants minus products. Okay, shoot. Then I probably will have to send out an email to correct that. Anti-bonding, that's on my test tomorrow. I don't know if you want my definition. Emily, send me an email. I understand anti-bonding, but I do not want to give you, with your testing tomorrow, I do not want to give you an explanation right now and it not be pinpointed, if that makes sense. Send me an email with just like a general, what you kind of want to know. And I will truly send you like a paragraph of an answer. I just do not want to sit here and give you an answer and let you sit with that and keep that and that not be an exact true definition, if that makes sense. So, okay, someone wanted the last part of the last question really quickly. The N is coming from just the 5. The F is associated, we have 0 is equal to S, 1 is equal to P, 2 is equal to D, and 3 is equal to F. So that's how I did that. The imps of L is always equal to -L to 0 to +L. And so for that reason, I knew that it's -3 all the way to +3. For the m sub s, we can have either positive or negative spin. That's because they don't specify which orbital it is in or exactly which electron it is. So for that reason, we can have both positive or negative spin. Can I go over the last question on the first page? Absolutely. Oh yeah, the valence one. Do not email me every day about 1308. You can email me every day about 1308 if I end up doing 1308. But if not, do not. Every now and then it's fine. I've really enjoyed y'all this semester. Okay. Can you work through another enthalpy program? I think I meant problem, but with the one answer. Are you talking about this one, Yasmin? Better change your email than LL. Yeah, it's 9:10. I really don't want to work an enthalpy problem, but if you drop one in the chat, I'll see. The one before it is with the maximum number of electrons. The one before it with the maximum number of electrons. Okay. What is the maximum number of electrons in an atom that can have the following set of quantum numbers? Good question. Okay. Andrew, just email me and I'll kind of give you the rundown on that. That's all I'm gonna say. Okay, so basically there's only one ever element. We know that there's many elements that can fall in n equals 4, right? We understand that. As well as there are many elements that can be a period 4 with an L of 3, right? Because an L of 3 is representative of that F block. Because 0 is S, 1 is P, 2 is D, 3 is F. So we can have a N4 with an L is equal 3, and there have a lot of them because we're technically going to have 14 electrons. 14 potential electrons have this. Okay. However, when we add that -2 of m sub L, this is what I was talking about earlier. I'm just going to kind of erase this, just kind of like redraw it. This is what I was talking about earlier with that m sub L is talking about a specific orbital. The reason we have from -L to positive L is because we have that -3, -2, -1, 0, 1, 2, and 3. That -L to positive L is telling us how many orbitals, as well as that each like negative and positive one is representative of an orbital, but that -3 and +3 are just opposite of each other. So in saying that, now if we have a -2, there's only 2 potential electrons that can fit in there. However, now if we add just a spin of +½ we now take away that whole negative sign, that down spin. So now we're just left with just that up spin. Does that help? Does that kind of clarify it? How we do start off extremely broad. There's a million electrons in just n equals 4. Once we get to that L of 3, we know we're in the F block. With that m sub L, again, that tells us there is potentially a lot of electrons that can be in that orbital, but that specific -2 is telling us about a 1 orbital, and that 1 orbital can only have a max of 2 electrons. And because we're given a specific spin, therefore it must be 1 singular electron. Had they just said n equals 4, L equals 3, and ml is equal to 2, this has 2 potential electrons. Okay, I hope that helps. Yep, I'll be doing SI pack, or I'll be doing finals prep exams as well as I'll continue on like normal SI stuff on Monday. So yeah, but I will be doing final stuff as well. Are you a little confused about ground state electron configuration? Okay, so basically all ground state electron configuration is just accounting for every single electron in the periodic table. As we started at hydrogen, it has 1 electron. As we increase from the periodic table, we add 1 proton and 1 electron at a time. So for example, hydrogen is just a 1s1. Oh, sorry, 1s1. 1 coming from n equals 1. This is n equals 2. The periods represent the n. The s is because it is in the s block. And the 1 is denoting the amount of electrons that came from that s block, just that 1. However, helium is going to be 1s2. Again, still in that first period, still in the s block, even though it is technically on the right side, it is still an s element, but we now have a superscript of 2. However, the full ground state, we want to do this for every element. So for example, if we wanted to go to fluorine, we want to account for every single electron before it. So for example, we will have 1s2 to count for both hydrogen and helium's electrons. We have 2s2 to count for lithium and beryllium's electrons. And then we will go to 2p, now crossing over to the p block over here. We want to go to fluorine. So let me kind of erase some of this to kind of give you a little bit more to look at really quickly. We're trying to get here, and that is going to be the 1, 2, 3, 4, fifth element in the p block. And so for that reason, we will just put 2p5. Again, because it is the fifth electron in the p orbital. We add one electron every single time. Does that kind of help with electron ground configuration on how it's like 1s2, 2s2, and then 2p6? Okay, perfect. Nice. Perfect. Okay. I'm going to scroll through again. If you still have a question, drop it in chat. I'm probably not going to stay longer than like 5 more minutes. You were confused as to why KF2 wasn't polar. Okay, so let me try to draw in 3 dimensions really quickly. Okay, so we've got our K. So in reality, I would like to think of it looking at it like this. So we have, it's linear. So they're basically stacked up on top of each other. However, for our electron pairs, I'm going to kind of do it like this. And I'm going to kind of draw these little ones kind of smaller in the back, kind of making them back into the page. And then these two kind of bigger, representing them kind of more close to us. So this right here, I'm going to try to make it a triangle. This is planar. And so all those electrons are just localized in the center. We have fluorine at the top pulling up and fluorine at the bottom pulling down. And the center, that is just spherical. It's not pulling any which way, as well as it's not contributing to a net pull up or down. And so for that reason, we have a net dipole here for the fluorines of just neutral, as well as we have a circular planar part from the electrons in which there is no net direction, because again, it's just circularized. It's pulling in a, quite literally in a triangle. We have pulling 2 this way and 1 that way. That truly equals out. So that is neutral in the middle plane. And then above the plane, we do have a pulling up and a pulling down, but because those are equal but opposite, we have nonpolar. Does that help? Perfect. Absolutely. Thank you for asking the question. Okay. Anyone else got questions on anything? If you're still on here for the person asking about the antibonding, still send me the email. I want to answer your question. I don't want to leave you hanging. I just want to make sure all my information is right on my end. Of course, Ruth. Thank you. Yes, literally, Ruth, if you invite me to play Among Us, I am saying yes. Like, that sounds like a ton of freaking fun. Technically, well, yeah, I'll be home this weekend. I leave Sunday to go out of town, but yeah, just hit me up. Yeah, you got a few ways to contact me. Is antibonding on the Chem 3? Not on the regular. I believe that antibonding is going to be for probably honors. Y'all probably will see antibonding here in a second. It's gonna kind of feel at times like orbital diagrams where we're gonna end up doing like this thing where we like go up and we have like pi bonding regions, and the bottom is like anti-bonding regions. It's technically like an area of like no like electron density. So thank you, Ruth. Yeah, everyone have a good Friday, Junior. Woo! I have 1 test and then I'm done. So it's gonna be a good week, y'all. Chase, you got a question?
Would you mind if I ask a quick question?
Go for it.
So on the reactions, the bond energy reactions, okay? What equation did you use? Did you do products minus reactants?
You said on the bomb equation?
On the bond equation, yeah.
The bond equation. Yeah, originally I did do products minus reactants. However, it is reactants minus products. I actually need to check in. Yeah, exactly.
Yeah, I watched a video by my teacher, right? And what she did was, here, I'll pull it up real quick. What she did was she did change of H, so like a change of H reactants, okay? Plus change of H products. and she like multiplied change of agent products by -1. So I guess that's the same thing.
That's honestly probably how I should have explained it. I think that's probably simpler than how now that I did it wrong, it's simpler. Yeah, I mean, that way 100% works. I think that's easier too, just to keep everything positive and then just multiply by -1 for the product. So, other X, whatever. So, yeah, I would go like that. I think that's the easier way. I'm probably gonna end up having to send out an email tonight correcting it because I think I have it wrong on my review sheet as well. So I might end up explaining it that way, honestly.
Gotcha. So. And do you think there's gonna be a lattice problem on the test?
Say it again.
A lattice energy problem?
Do I think there'll be a lattice energy problem? I think there may be an example where, let me just give you an example really quickly. Where they're gonna like probably compare to, they may give you like lithium fluoride and beryllium oxide. Beryllium oxide is gonna have higher lattice energy. And that is because the separation of charge, beryllium's a 2+, oxygen's a 2-, lithium's a plus, and fluorine's a negative. We do play a little bit into size at times for lattice energy. However, I kind of mentioned it a little bit earlier. I really kind of skid over it though. But I highlighted size, but charge is definitely like our trump card for importance of lattice energy.
Because isn't it charge plus charge on the top and then atomic radii on the bottom or something like that?
Yeah, I think it's actually like the charge is multiplied on the top divided by additions of radius on the bottom.
So basically look for stuff that's bigger charge, and that's probably your most lattice energy.
Exactly. That's going to be, if I was taking the test, the second I saw like a 2+ and everything else had like just minus or plus ones, yeah, that's the answer. Simple.
Okay. I appreciate it. Thank you for staying a little longer.
Absolutely, Chase. Thank you for asking your question.
You have a good night.
You as well. All righty, everybody. You have 2 exams. Praying for you, Liana. Truly sending good vibes your way. I'd said it Monday, but it is a stressful time of the year, so everyone please try to keep good mental health. Do something every day to try to just keep yourself sane. Again, it's Thanksgiving. I don't know anyone's family dynamics or traveling to hometowns, but for a lot of people that causes a lot of anxiety. So just be there for yourself during this test week. It's already hard enough to have a Chem 1307 exam, but it makes it even harder with the world we live in right now. So please take care of yourself. And goes for everybody. So I love you guys. If you need anything or just need help or someone to talk to, like, just reach out and I got you. Not COVID. We stand that, Claire. At least it's not COVID. But you'll be okay. Press through. Work hard this week. So next week it will feel so sweet when you can look back and say, damn, I did good and now I get to rest. Fight for that feeling. Really. Seriously. I like to tell people, like, for me, I have like a reason in my heart why I'm fighting to go to med school and fighting to do like everything to the degree I do. And I like to tell people, like, if you don't get that feeling and that feeling doesn't choke you up at times, like, you're not doing it for the right reason. So like, you should want to get an A on this test so bad. Like for me, like, I will literally like, at times drive myself to tears, like studying, because I want it so bad. So if you haven't hit that point yet, if you haven't really broken, I'm not gonna say broken down, but if you haven't had that moment of like, I want this so bad and I'm struggling, you're not trying hard enough. You need to find that and you need to give it your all. It's not an easy journey. It is a hard journey, but we want it to be rewarding. So give it your damnedest and it'll all pay off. So yeah. Yep, -61 is the correct answer. I don't know if I didn't highlight it, but yes, -61 is the correct answer. Ruth, I think you've been literally asking that a million times and I have literally just been ignoring you. But yes, it is -61. No, you're good. It's me who's apologizing. But